Let's have a go at actually deriving a master equation. So we'll start off where we've got a system and a reservoir, and the Hamiltonian for the combined system is of course going to be the Hamiltonian for the system plus the Hamiltonian for the reservoir plus the interaction. And you may recall that you can go into different pictures. You can go into the Heisenberg picture or the Schrödinger picture. Well, if we go into the interaction picture, then we can make the dynamics for the system Hamiltonian and the reservoir Hamiltonian, which only act on their individual subspaces. We can suck them into the operators and then have our density matrix or our state only depend on evolution due to the interaction Hamiltonian. Now, notation. This SR means the density matrix for the combined system and reservoir. And this I means we're in the interaction picture. Of course, without this interaction term in the Hamiltonian, our dynamics is trivial. Our system evolution and our reservoir evolution are completely separate, and so we can solve for our reduced density matrix without even thinking about the reservoir at all. So this interaction Hamiltonian has all the difficult parts in it, and that's why we use the interaction picture to really focus in on what that does. Now we can take this equation of motion for the density matrix and formally integrate it once, where we're explicitly allowing this interaction Hamiltonian to depend on time now, which it's going to need to do. Now it doesn't look like we've won very much here because we've got the density matrix as a function of time in terms of the density matrix at the initial time, which is good, but it's also in terms of itself. This is the density matrix as a function of time. So it looks like we've really kind of gone around in circles there. So what we're going to do is we're going to make it worse. We're going to take this solution here and we're going to put it back into there. Now what do we gain from that? It looks like we could just keep on going forever, and indeed we could, but we don't need to. The reason we went to second order there is that in fact there are many situations in which terms like this are actually zero when we trace them over the reservoir, in which case we can ignore that kind of term. In that case it's really only the second order term here that gives us any contribution to the derivative. So let's go ahead and work out the differential form of this equation again. And now we're finally ready to make our actual approximations. So remember, what we're actually targeting is the reduced density matrix. So we want to take the trace of the reservoir of this thing. So let's go ahead and do that. And because the trace and the derivative are both linear, we can pass one through the other. And the trace over the reservoir of this combined density matrix is exactly the reduced density matrix, which we're denoting by just this S here. So let's take the trace over the reservoir for the right-hand side as well. And now we can finally make our approximations. So first of all, we assume that our system was initially separable. In other words, second of all, we assume that this term here happens to be zero. And this is true for a lot of physical cases that we examine. And now we make the real doozy of an approximation. Suppose that our state as a function of time is also separable. This is a very strong approximation. Note that I've assumed that the reservoir doesn't change at all. The idea here is that the reservoir is so large that the system simply doesn't have the capacity to affect it in any significant way. This separability for all times is known as the Born approximation. Now we'll take this equation later and we'll apply it to some specific situations, and they will give us master equations that look just like the form we showed in the previous video.